Hi, today we're going to be covering electron configurations for SP and D blocks and orbital diagrams. So rule number one, there are 3 rules total that we'll need to learn when we're dealing with electron configurations and with orbital diagrams. The first rule is Pauli's exclusion principle, which some of you may already know. It's that 2 electrons can fit in each orbital. So just to remind you, in the S sublevel, there's 1 orbital. In the P, there are 3. D has 5, and F has 7. So if we multiply each of those orbitals by 2, it will give us our maximum number of electrons per orbital. Rule number 2 is the Aufbau principle. And it states that whenever you're placing electrons in a configuration, you have to go from lowest energy to highest energy. So according to this, the lowest energy orbital would be the 1s2, and then 2s2, and so on. Something interesting here is that we have 3s2, 3p6, and then it skips 3D because 4s2 is slightly lower in energy than 3d10. And in just a minute, I'll show you a trick to help you remember that using your periodic table. Rule number 3 is Hund's rule. Hund's rule states that when we're filling up orbitals, we have to halfway fill them before we start placing a second electron in any orbital. So you might remember that with Lewis dot diagrams, we did something similar to this. So if we were to take the Lewis dot diagram for oxygen, we would place 6 dots around, but first, before we put before we pair any up, we have to put 4 around so that they're individual. And then we can start pairing up. So that's the Lewis dot diagram for oxygen, and we have that same principle when we're drawing the energy orbitals, or the orbital diagrams for elements. So let's take a look at oxygen just for a minute and see if we can figure out what its electron configuration is and what its orbital diagram would look like. First thing that we'll need to do is figure out, well, how many electrons total do we have in oxygen? There are 8, assuming that it's not an ion, so it's neutral. So there are 8 electrons in oxygen. Now, if we go back up here and look at the Aufbau principle, it states that the lowest energy level is 1s2. So our first 2 electrons will go in the 1s sublevel. And this superscript means that there are 2 electrons in this sublevel. Okay, so we've got 1s2, then we'll have 2s2. I'm just following the same energy levels that we see with the Aufbau principle. So far we have 4 total electrons. We need 4 more, so the next energy sublevel would be 2p. And we only have 4 more electrons that we need, so we'll end with 2p4. So the electron configuration for oxygen would be 1s2, 2s2, 2p4. So now let's see if we can figure out its orbital diagram. Now, you might remember that there's 1 orbital in the s sublevel. So I'll draw a little line like this. That's the 1 orbital for the 1s. In 2s, it's an s, so it just has 1 orbital as well. So there's our 2s. And then the p group has 3 orbitals. So I'll draw 3 lines to show those 3 orbitals. This is the 2p sublevel. In the first energy, so in 1s, we have 2 electrons. So I'll draw each electron like a little half arrow. So here's my first electron that's in 1s, and there's my second electron that's in 1s. In 2s, I also have 2 electrons. So I'll draw the first electron, and then the second electron. Now, according to Hund's rule, that will affect how I draw this 2p level. So I've got 4 electrons in the 2p. So I'll put one electron in, and now I'll put another electron in the second orbital, and then another electron in the third orbital. Notice I have to halfway fill up all of the same energy level orbitals before I pair any up. So now that they're all filled halfway, I can go on and put my fourth electron in. So this would be my electron configuration for oxygen, and this is my orbital diagram for oxygen. Now the periodic table is arranged pretty nicely, and it helps us to write the electron configurations and to draw the orbital diagrams. So here's the periodic table, and it's somewhat divided already into the different sub-levels. So you have an S block. The S block is shown in red. The D block is shown in green. The P block is shown in white, and the F block is shown in purple. Notice that helium, it's off here to the side. Oops, sorry about that. Helium is off here to the side. It's also considered part of the S block. So when we're doing helium, we just sort of assume that it's right here. Okay, also keep in mind that the row numbers indicate the energy levels. So this first row would be energy level 1. The second row would have energy level 2. Okay, so now that we use that, let's figure out the electron configuration by reading through the periodic table until we get to the element that we're trying to deal with. So let's take a look at hydrogen. Hydrogen is located right here on the periodic table. It's the first element. So the energy level is 1. It's in the S block, and there's just one electron there. So the electron configuration would be 1s1. 1 stands for the energy level. S would be the sublevel. And that second one is talking about the number of electrons in the sublevel. So if we were to draw the orbital diagram for hydrogen, we would need to have one orbital for the S, and there's just one electron in it. Now let's try beryllium. Beryllium is located right here on the periodic table. So we need to read across the periodic table until we get to beryllium. We'll start at the very top corner where hydrogen is, read across until we get to beryllium. So when I start, I'm going to start with 1, energy level 1, in the S block, and I'll count over twice. 1, 2. So there's 2 electrons there. Then I'm in energy level 2. So I start with 2, I'm in the S block, and I have 2 electrons until I get to beryllium. So let me show this to you one more time. In energy level 1, I have 2 electrons, or 2 elements that are before beryllium in the 1s group. So I have 1s2. In the second energy level, I also have 2. So I'll have 2s2. This 2 right here comes from the number of electrons that are in the 2s sublevel for beryllium. You can also remember it by counting how many elements there are up until you get to beryllium. Okay, let's try fluorine. Fluorine is located right here on your periodic table. So let's read across. When we're reading across, we'll have 1s2. Then we'll have 2s2. And then we'll be in the 2p. 1, 2, 3, 4, 5. So 2p5. And to do my orbital diagram, in the 1s, s has one atomic orbital. 2s2 also has one atomic orbital. So that's my 2s. This is my 1s. And 2p has three atomic orbitals because it's a p, and p's have three atomic orbitals. In the first orbital, so in 1s, I have 2 electrons. In 2s, I have 2 electrons. And in 2p, I have 5 electrons. 1, 2, 3, 4, 5. And I just realized I left you hanging with beryllium, so let's do its orbital diagram as well. In the 1s2, there's 1 orbital. And in 2s, there's also 1 orbital. And there are 2 electrons in the 1s and 2 electrons in the 2s. Chlorine is located just underneath fluorine, right there on the periodic table. So if we start to read across, we'll have 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4, 5. And if we're going to draw out these orbital diagrams, we'll have 1s2, 2s, so the s has 1 orbital, p, so 2p would have 3 orbitals, then 3s would have 1 orbital, and 3p has 3 orbitals. So in the 1s we have 2 electrons, in the 2s we have 2 electrons, in the 2p we have 1, 2, 3, 4, 5, 6. In the 3s there are 2 electrons, in the 3p there are 1, 2, 3, 4, 5 electrons. Let's do 2 more examples. Okay, now potassium is located right there on the periodic table in row 4. So if we were to start this, let's start reading from the top. We'll go left to right, top to bottom. So first we have the 1s, and there are 2. I'll write it over here because these are starting to get long. Then we'll have 2s2. Now we have our p, so we'll do 2p, and there are 6. 1, 2, 3, 4, 5, 6. Then we have 3s2, 3p6, and 4s1. There's your electron configuration. Now let's do the orbital diagram. In the s sublevel, there's 1 atomic orbital. So I'm going to draw 1 for each of my s's. In the p, there are 3. Here's another s. Here's another p. And then my 4s. There are 2 electrons in 1s. There are 2 electrons in 2s. There are 6 electrons in 2p. There are 2 electrons in 3s. There are 6 electrons in 3p. And then there's 1 electron in 4s. Okay, now let's move on to germanium. Okay, germanium. Germanium is located right here. Now this gets a little tricky. And before I get into this, I want to remind you guys of something. In the energy level 1, we have the S sublevel. In energy level 2, we have S and P. In energy level 3, we have S, P, and D. And in energy level 4, there's S, P, D, and F. Okay, but take a look at something. In the third energy level, there is no green. Do you see? In the third row, there is no green. So instead, we have to drop down a level. So all of this in here is really 3D. This is considered 4D. This is 5D. And this is 6D. Okay? And then the F group does something similar too. On your periodic table, you might see that the F fits in right here. And so really, that would be like row 6. But instead, energy level 4 is where the F starts to take place. And we'll talk more about this in the next lecture. This is just to give you a little taste of what's to come. And so for the F group, you need to subtract 2 from the energy level. So this is really 4F. And this is 5F. But when you're recording it, you still go in order of the periodic table. Okay, so I'm going to go on and erase my notes there so that we can use it to track our progress to get to germanium. Okay, so again, germanium's right here. We're going to start off reading across. So there's my 1s2. Here's my 2s2. Next is 2p6. Then we have 3s2. Then 3p6. 4s2. And this is where it gets tricky. Remember, this is our first D sublevel. So this is called 3D. So then we go through our 3Ds, and there are 10 electrons in the 3D. And now we have to go back up because this is our 4p. So we go back up to 4p, and there are 2 electrons before we get to germanium. So this is our electron configuration. To do the orbital diagram, S has 1 orbital, 2s has 1 orbital, 2p has 3, 3s has 1, 3p has 3, 4s has 1, 3d has 5 orbitals, and then I'll erase this just to give us a little more room, and 4p has 3. So for this orbital diagram, we would have 2 electrons in 1s, 2 in 2s, 6 in 2p. We have 2 electrons in 3s. We have 6 electrons in 3p. We have 2 electrons in 4s. We have 10 electrons in 3d. And then we have 2 electrons in 4p. And remember, because of the Hund's rule, the electrons will fill up individual orbitals halfway before they start to pair up. And on your homework, in case you are one of our KHS students, on page 12, instead of OS, I, and TL at the bottom, please change those so that they are RU, I, and TI. Again, that's RU, I, and TI. Good luck!